Hi, this is Dr. Bay, and here's Bugsy, and today we're going to go over ways to synthesize ethers, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Ethers are compounds that contain an oxygen atom bonded to two R groups, where each R group can be an alkyl, aryl, or vinyl group. Ethers can be found in many molecules found in nature, as well as many drug molecules. Some examples are melatonin, which is a hormone that regulates the sleep cycle, propranolol, which is a medicine that's used to treat high blood pressure, and morphine, which is used to treat severe pain. There are actually two different methods for naming ethers, both of which are equally acceptable. The first way is to identify the R group on each side of the oxygen atom, arrange them in alphabetical order, and then add the word ether at the end of the name. In this example, let's identify the groups on each side of the O. To the left, there are two carbons, which means that this is an ethyl group. And then to the right, there is one carbon, which means it's a methyl group. Since the E in ethyl comes before the M in methyl alphabetically, we're going to list the ethyl group first and then the methyl group second. So the name of this molecule is ethyl methyl ether. Let's name another molecule. To the left is a methyl group, and to the right is a tert butyl group. Remember from IUPAC naming that we use the B in tert butyl for alphabetizing. So in this molecule, tert butyl will actually come first and methyl will come second. So the name of this molecule is tert butyl methyl ether. The second way of naming ethers is a more systematic approach. The larger R group becomes the parent chain, and the smaller R group becomes an alkoxy substituent. The two parts come together as one long word. Now keep in mind that the oxygen atom of ether is always part of the alkoxy substituent, not the parent name. In this example, let's identify which side is larger, which would make up our parent chain. Since the right side contains 5 carbons, this parent chain name is pentane. That means that the left side, including the oxygen atom, is the alkoxy substituent, which always has an oxy ending. Since it contains 2 carbons, this is called ethoxy. So the name of this molecule is ethoxypentane. In the next example, the left side is larger, so that'll be our parent chain, making the right side the alkoxy substituent. So the name of this molecule is methoxycyclohexene. Now that we know how to name ethers, let's go over different ways to form an ether. Williamson ether synthesis is a two-step mechanism that includes a proton transfer with a strong base, such as sodium hydride, followed by an SN2 nucleophilic attack. Keep in mind that this reaction forms an ether by increasing carbon count. In this example, 2-propanol is reacting with sodium hydride, and then with ethyl bromide to form the following ether. The mechanism starts with a hydride deprotonating the hydrogen from the hydroxyl group, and the OH bond breaks to form a new lone pair on O. Then O- attacks the alpha carbon of the electrophile, and the bromine-leaving group leaves, which then forms our ether product. And before we discuss the next way to form an ether, let's quickly review oxymercuration-demercuration across a pi bond. Recall that this particular reaction follows Markov-Nikov's rule, where the OH adds to the more substituted side of the alkene, while HgOAc adds to the other side. Also, this reaction follows anti-addition of the H and OH across the pi bond. The mechanism of this starts with a pre-step where one acetate group leaves to form HgOAc+. In the first step of the mechanism, HgOAc+ adds across the pi bond in a concerted one-step way to form a mercurinium ion. Then our nucleophile, water, attacks the more substituted carbon and adds as the opposite bond type as HgOAc, and then the carbon-mercury bond breaks to form a lone pair on Hg. Once the alcohol group is added to the more substituted carbon, then sodium borohydride is used to undergo demercuration to form the following product, plus its enantiomer. Now we're going to learn about alkoxymercuration demercuration across a pi bond in order to form an ether. The general scheme is super similar to the last reaction, except instead of using water as our nucleophile, you can use any alcohol such as methanol or ethanol to form an ether. This reaction still follows Markovnikov's rule and is anti-addition of the H and OR groups, just like oxymercuration demercuration follows. And the mechanism is also super similar as well. In this example, this alkene is reacting with mercury diacetate and ethanol in the first step, and then sodium borohydride in the second step to form the following ether product. The mechanism of this starts with a pre-step where one acetate group leaves to form HgOAc+, and then HgOAc+ adds across the pi bond in a concerted one-step way to form the mercurinium ion, and then our nucleophile, ethanol, attacks the more substituted carbon and adds as the opposite bond type as HgOAc, and then the carbon-mercury bond breaks to form a lone pair on Hg. Once the ether group is added to the more substituted carbon, then sodium borohydride is used to undergo demercuration to form the following ether product plus its enantiomer. Ethers are normally quite unreactive in basic or mildly acidic conditions, which is why they're an ideal solvent for a lot of organic reactions. But when an ether is heated with an excess amount of a strong acid, the ether will undergo acidic cleavage, where it will be converted into two alkyl halides. In this example, ethyl isopropyl ether reacts with an excess amount of HBr in heat. The mechanism starts with one of the lone pairs on O attacking the H in HBr, and the bond forms a new lone pair on bromine. Now think of the protonated oxygen as a good leaving group. Br-, which is a strong nucleophile, attacks one of the alpha carbons and the carbon-oxygen bond breaks so the leaving group can leave. This forms the following alkyl bromide. Now the Br- nucleophile could attack the other alpha carbon to form a second alkyl halide as well. In both of these cases, an SN2 mechanism was followed since both alpha carbons were either primary or secondary. But if the alpha carbon was tertiary, then this would follow an SN1 mechanism instead. In summary, you learned two different methods for naming ethers. The following molecule can either be called ethyl methyl ether or methoxyethane. You also learned two ways to form an ether by Williamson ether synthesis or by alkoxymercuration demercuration. And lastly, you can convert an ether into two alkyl halides using an excess amount of a strong acid in heat.
Organic.